Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 5.6, and let me start by trying to finish up what we were talking about in the last module. If you remember, what we discussed was this system of spins, and if you had them all up and then let them become random, then the process would involve an increase in entropy corresponding to a decrease in free energy. And as I mentioned, what the second law says is that in principle, you could extract that amount of free energy as useful work. It doesn't quite tell you how you do it, but you say in principle you could do it and second law would still not be violated. Okay. So I guess at the end of that last module, what I tried to give you was an idea of a device which could in principle do just this. And the idea was that it's basically an anti-parallel spin valve, a perfect anti-parallel spin valve. And what happens then is you start out this system of localized spins looking all up. And every time one of these flips down, these localized spins, the electrons in the channel, there's an electron that gets flipped up because of a process. This is called this exchange interaction. It should look something like this, that an up localized impurity and a down electron kind of interact to flip both of them. So the up impurity becomes a down impurity and the down electron becomes an up electron. And the way we have constructed the device is that that up electron can only get out from the left contact. And the empty spot that was left behind for the down can only be filled in from the right contact. And so this gives you a flow in the external circuit with which you could charge up a battery or do something useful with it. See? And what I show, I guess in the notes, this is in lecture 17 of the notes, I believe, that by analyzing, starting from this and analyzing exactly how much the open circuit voltage would be and how you'd extract energy from this battery that we have constructed out of these all up spins. What you could call a information battery sort of, one that actually takes information and turns it into work. And I show how you could, by analyzing it, that the maximum amount of energy that you could extract from it is actually nkt log 2, as required by the second law. But I won't go through that part of the derivation. That's in the notes, you can look up. Instead, let me bring up one conceptual point. And that's something like this. I said that when it's all up, the entropy is 0. And when it's randomly up and down, the entropy is nk log 2. But what if you had a collection of spins that were not really all up, but were, somewhere up and somewhere down, but you knew exactly what it was. In other words, you knew that, this one's down, that one's up, this one's down, that one's up. You knew exactly what it was. Thus, in that case, you see its entropy is not nk log 2. nk log 2, that entropy comes from the fact that there are many, many configurations and it's in all of those with equal probability. So there's nothing so special about having all up. The important thing is knowing what it is. So if I had a system of spins which was not really all up, but some up, some down, and I knew exactly what it was, would I still be able to extract energy from it? And I believe answer is, in principle, yes. You'd have to build a much more complicated device. In the sense that it would be something like this, that supposing you have a bunch of spins, some of which are up and some of which are down. So you have a whole bunch of these here, and let's say these ones happen to be up, and here we have a few that are down. I'm trying to draw down. some up and some down, and I know exactly what it is. Well, so in principle, I could kind of build this kind of a device around this one, in which case the left-hand side would be negative, left-hand contact, and that side would be positive, because these are all up. And so every time it flips one of these flip, it creates an extra up electron here, which comes out of this contact, and if you don't let it flow, it will build up here, giving you a negative charge, negative voltage. On the other hand, if I build another battery here, because these are all down, it will create a potential that is like negative on this side and positive on this side. And of course, if I just connected them together, I wouldn't get much of a voltage, open circuit voltage. Why? Because this is minus, that's plus. But since I know exactly what it's going to be, I could, in principle, I think, connect these two negatives together and connect the positives together. You see? And again, get a battery that gives me an open circuit voltage with which I could charge up do useful work. So the point I'm trying to make is, if you know exactly what it is, in principle, you could build extract the energy. Now, device is getting more complicated, and as I stressed, all this is really more from a conceptual point of view. It is not as if, and from a practical point of view, it is not like if someone sent you a bunch of spins with some information in it and you had no use for it, you'd actually want to build a device to extract the energy. It probably wouldn't be worth the effort. But it's more like, as a matter of principle, what it shows is information can in principle be traded for energy. And so this kind of connects that idea of Shannon entropy, which measures information, with this thermodynamic entropy, which has a dimension, the one we have been talking about, and shows that, that if you had information, you could trade it for energy. Okay. So now the next point I wanted to mention is, again, in this field, another thing you'd hear a lot about is this Landauer's principle, which sort of says that, well, if you had a bunch of spins that were in some random directions, and you wanted to put them all in the same direction. So you have a bunch of spins, all random, and you want to put them in a known state, all up, say. That would be kind of corresponding to erasing whatever information was in there. Whatever was there, erase all history, put it in a state you know. That will require a minimum energy of nkt log 2. That's the Landauer's principle. And the way you could connect it with what we just discussed could be something like this. That let's say, in order to go from here to here, I need an amount of energy, say E. But of course, once I'm here with all up, as we just discussed, I could, in principle, extract nkt log 2 out of it. You see? Because once I know they are all up, I could build a device to extract nkt log 2. And so it seems that in order to be consistent, I must need at least nkt log 2 to go from here to here. Because you see, otherwise, I could have a cyclic process where I don't spend any energy, turn this into this, and then extract energy. That way you would be able to create energy out of nothing. See? So just to be consistent, it seems that since you can extract nkt log 2 from it, it means that to put it in that state in the first place should require you to spend nkt log 2. And that's kind of the Landauer's principle, that if you want to erase the information, you need at least nkt log 2. Now, another thing you'd see a lot in the literature, something called this Maxwell's demon. And that's actually a very vast literature, you'll see. A lot of discussions on that. And actually dates back to Maxwell, back in the 19th century. And that, usually the simplest version would be something like this. That you have a box where you have gas molecules all running around with different velocities. For this discussion, you could assume that some are hot, in the sense they have a lot of energy, and some are cold, in the sense they don't have as much energy. And ordinarily, they would all be evenly distributed. There would be some fast-moving ones here, some fast-moving ones on this side, and so on. And if you had a demon who kind of knew what the velocities of each thing was, what it could do is open a trapdoor here and let all the hot molecules collect on one side and the cold ones go to the other side. So it's like every time it sees a hot molecule, lets it go this way, cold molecules lets it go that way, and thereby create a temperature difference. And of course, once there's a temperature difference, you could extract useful work from it. And this is something you could kind of map into the problem we just talked about. You see, you could think of hot molecules as being, say, the up spins, cold molecules as being the down spins, and the left side and the right side as being these two contacts of your anti-parallel spin valve. And the Maxwell's demon, of course, is these localized impurities, which is, when it's doing all this, it's kind of trading information for work. So just as here, if you start out the spins in some very special state, then it can trade that information as it gets random and do work. Similarly, here also, if the demon starts out in some, all charged up, ready to go, then it can do this kind of thing for a while. But eventually, of course, it will all die down, all die out, just like the spins, unless it's replenished with other things. So that's kind of the view that people have. And what I was trying to show here is that although this is phrased in a very different language, and you'll see a lot of it in the literature, you could map it onto the device that we just talked about, which I kind of introduced here because it connects up to many of the concepts we have talked about in this course, the spin valve and the spins and how they interact. And you can see that in terms of these devices, you can understand many of these deeper issues that people talk about in the literature. Of course, these days, a lot of the discussion is more about the quantum aspects of this. What I mean by that is, as you know, in general, in this course, the part 1, we talked about everything within a semi-classical framework, where you think of electrons as particles, don't worry about the wave nature. We didn't really bring in the Schrodinger equation, so on. That was the part 1. Part 2 was largely about the quantum things. This is where we kind of started week 1 with Schrodinger equation. And the first 4 weeks have been entirely about the quantum part. But this week, we really talked more about everything from a semi-classical point of view. We didn't quite have time to get into the quantum aspects because a lot of these concepts are totally new. And of course, first thing you need to clear up and be clear on is the semi-classical picture before you get confused with the quantum things. And so much of this week we have spent essentially discussing all the semi-classical aspects of this. So for example, you see, when I say that up plus down, this up impurity and a down electron interact to give you a down impurity and an up electron. Quantum mechanically, what happens is something like this, that you have an up electron and a down impurity. That's the initial state. That's the initial wave function. So you have to think of your electron and impurity as one big system. So that's this thing, and they interact. And in the process, it then goes into a state which is like a superposition of up, down, and down, up. I guess if I want to carry on the color coding, I should keep that. I've generally been trying to write the ups with the red, but I guess you see the point. So the main point I want to make is at first when they interact here, it goes into this superposition. It has a wave function that is a little bit of this and a little bit of that, right? It need not be equal amounts, but for this discussion, let's assume it's 1 over square root of 2 of this and 1 over square root of 2 of that. And the interaction puts it into this state, but what you can show, and this is discussed in this last tutorial. We'll go into the math a little more in detail in the last tutorial, where I show that whether the system is in this state or this state doesn't really increase the entropy. Here also the entropy was 0. Here also the entropy really remains 0. Because in a way, you could think of, I mentioned in the last week, at the end of last week, I mentioned that one of the nice things about the spin formalism that we learned is that there are all kinds of systems that are physically not quite single spins, but you could understand them or visualize them in terms of these two spin components. So conceptually here also, this is a spin and that is a spin, but I could take this whole thing and view it as, say, an up component, and call this whole thing, say, a down thing. So in that case, what has happened is something that was 1, 0 has become like 1 over square root of 2 and 1, 1. In the sense it is like 1, 0 plus 0, 1. And that, if you may recall from this week 4, is like taking this quasi-spin. I mean, this is not real spin, but it's something that was pointing in the z direction and turning it in the x direction. And just turning a spin doesn't increase its entropy. Entropy is increased when it gets randomized. When it started out this way, and after you're done, you don't know which way it is. If you just take something that was like this and put it in this direction, that doesn't increase entropy. You knew exactly what it was and you still know exactly what it is. It's just that it's something else. That's all. So when exactly then does the entropy increase? Because as we discussed, in the process of this becoming random, somewhere the entropy increases. And that's where I believe the answer is that that happens when this electron here actually escapes into the contact. So once it escapes into the contact, that's when basically the wave function collapses and you have a 50% chance it will escape into the down contact, a 50% chance it will escape into the up contact, which means there's a 50% chance the eventual wave function will be this, 50% chance eventual wave function will be this. And you do not know which one. And that is when you'd say that the entropy actually has increased. This I'll talk a little more about in this tutorial, and my thoughts, it's all in the lecture notes also. But I just wanted to mention here that these are aspects we really didn't have time to get into. Because, as I said, this week we were largely focusing on the semi-classical part of it. And if you look in the literature these days, there's a lot of interest in this quantum information and all the possibilities that one envisions in those contexts. And there are many concepts related to all these. So to sum up then, I guess, started right at the start of the course, from the very first scientific overview, I'd mentioned that transport processes, what really makes it very difficult and conceptually complicated is that there are these two types of processes that are intertwined. The mechanical ones, which are force-driven, the ones we kind of usually understand a little better. And then there is this entropy-driven things. And this entropy-driven part we didn't talk much about, because we said that, well, the great thing about nanoelectronic devices is that it's a very good approximation to say that all entropy-driven things happen in the contacts. And if that's true, then what happens is you can handle all that just by legislating that the contacts are always maintained in equilibrium with the Fermi functions. And that way you can bypass all these complexities of the entropy-driven things. And in this last week of the second part, I've tried to give you a little bit of a flavor of what exactly this entropy-driven processes involves. That what it essentially is about is, usually in mechanical things, the force-driven things, you go from one state into another state. So it's sort of like you have a spin in this direction, you rotate it in another direction. So it's like there's no loss of information. Wherever you start, you go to another state. Whereas entropy-driven things is when you go from one to many. It's like you started out in something that there is only one possibility and you go out into many. And lots of things in life, like the flow of heat, is really governed by this entropy. It's the increasing entropy. Why does heat energy flow from hot bodies to cold? Well, again, the argument would be because that's how the overall entropy can increase. And so it means you're going from few states to many states. The energy is getting distributed. So that's the thing we sort of discussed in this last week, in the last module, last week of this course. But by and large, what we have talked about is very advanced concepts. You could call it, non-equilibrium statistical mechanics, involving some of quantum statistical mechanics, this NEGF method that we talked about. Talked about very advanced concepts here, but what has allowed us to do that in a relatively elementary way, because normally these formalisms take, many, many semesters of work to master. But I hope I was able to at least convey the flavor of it, what is involved. And again, what allowed us to do this is this very nice situation in nanoelectronics where this entropy-driven things and the force-driven things are spatially separated. So those are the broad ideas I tried to convey in this course, and thank you for your attention.